Students, good morning. Today I am going to solve one more problem. The problem comes under the category of applications of first of thermodynamics to flow process, the to compressor. The problem is carbon dioxide enters in an adiabatic compressor at 100 kilopascal and 250 degree Kelvin at a rate of 0.1 meter cube per second and leaves at 500 kilopascal. So initial condition temperature T1 is equal to 250 degree Kelvin and initial pressure P1 is equal to 100 kilopascal. Similarly, T2 is not given and P2 final pressure is equal to 500 kilopascal. Volumetric flow rate VFR is given 0.1 meter cube per second. Carbon dioxide is assumed to be an ideal gas. CO2 is assumed to be an ideal gas. Determine the work of compression per unit mass for isothermal compression. Take adiabatic index. Index of adiabatic process is 1.4. This is given. Before entering into the problem, the first law of thermodynamics to the flow process. First law of thermodynamics to flow process is of m del V square, that means role of kinetic energy, plus mg del H, that means role of potential energy, plus changes in enthalpy del H is equal to Q minus Ws. Usually in industrial process, the role of kinetic energy and potential energy are assumed to be negligible. Their role is insignificant, hence these two terms are deleted from the equation. Hence the final equation del H is equal to Q minus Ws. When process is reversible adiabatic, when process is reversible adiabatic process, changes in heat content is constant, changes in heat content is equal to 0. This equation in differential form, dH is equal to dQ minus dWs. This term gets cancelled, hence del H is equal to minus Ws. Since it is a reversible adiabatic process, the work done or changes in enthalpy is at constant entropy. That means isentropic process. This work, shaft work, is called as isentropic work, or minimum amount of work required for the compressor to compress the gas from initial condition to final condition. This is the equation for reversible adiabatic process. In our problem, it is a reversible isothermal process. Isothermal process. Isothermal for an ideal gas, changes in internal energy is the function of temperature only. Since this process is isothermal, then changes in internal energy become 0. Also, changes in enthalpy is equal to 0. How? Listen, this is H is equal to U plus PV. On differential form, dH is equal to du plus differentiation of P into V. This PV is nothing but N into R into T. Hence this equation du plus N R dt. Changes in temperature is 0. Changes in internal energy is 0. Hence changes in enthalpy for an ideal gas is equal to 0. Changes in enthalpy for an ideal gas is equal to 0. Hence this term becomes 0 for reversible isothermal compression process. The remaining term Q minus Q is equal to Ws, that is equal to P into dV. For an ideal gas, PV is equal to N into R into T. So Q is equal to Ws is equal to N R T what is this? Instead of P I am going to write nRT by V, 1 by V into dV. That means nRT ln V2 divided by V1. For an ideal gas, P1 V1 by T1 is equal to P2 V2 divided by T2. This is the isothermal process. Hence T1 and T2 are cancelled. I am in need of V2 divided by V1. V2 divided by V1 is equal to P1 divided by P2. Now I am going to substitute this information here. Q is equal to W is equal to N R T into ln P1 by P2. This is the required equation to solve our problem. Okay. Our problem is reversible isothermal expansion. Reversible isothermal expansion. In order to estimate the amount of work required for the compressor, Q is equal to W is equal to N R T ln P1 by P2. There, so N is equal to 1 mole, R is equal to 8.314 joule per mole degree Kelvin into temperature 250 degree Kelvin into ln P1 100 divided by 500. The answer becomes minus 3,345 minus 3,345 joule per mole. In order to cancel mole, you have to divide by molecular weight. 44 gram per mole. The answer is equal to minus 76 joules per gram. This much joules of energy or work required for the compressor to compress carbon dioxide from a given pressure of 100 kilopascal to exit pressure of 500 kilopascal. This is a simple method to find the reversible isothermal compression process. Thank you.